Hello guys and welcome back. So let's use our mouse movement to control the rotation of the camera. Okay. So far what we have is to use these attributes. So we need to update those things, right? The camera direction especially, right? To make a change when we move the cursor. Okay. Now again, be aware that this is kind of like a reversed effect. Because again, camera doesn't move. It's we're moving the object basically, right? So basically, we're rotating other things in the opposite way. So when you're thinking about your math, you think of it in a reversed way, if that's easier to kind of understand. But yeah, we are gonna have to go ahead and calculate rotation in kind of like a reversed order, if that makes sense. Okay, so let's go ahead and take a look at that. Okay, so we need to keep track of where the cursor is, and there's a function we can hook up with, which is just glfw glfw cursor position callback, right? Passing window, and also we need to pass in a function pointer. If we go take a look at that function pointer is of the type that returns void, nothing. So we need to create a function for that. Okay, I'm gonna do it in here. So I'm gonna say void cursor moved. Okay, and then have those in there, and then it's window involved, and then X position and Y position. It would be better if they read the documentation better in their code, because sometimes you just don't know what those two doubles mean. You can only guess or you Google search, right? Some very good documented program or library will actually have those things marked down. Hey, parameter A, parameter B, what do they do? I really like those really detailed documented code, like Unreal Engine, for example, does have a very detailed description on every variable there that worth mentioning. Anyway, so let's just check, right? If that's the case, so we can do std out, X position, and then maybe have a comma in the middle, and then Y position. And let's see if we're getting the right thing. Right, I'm gonna run this. Oh, actually, I haven't even passed that in yet. So I'm gonna copy that and put that into the function callback in the glfw set cursor position callback. Run this again. Right, now we can take a look at the value here. Indeed, right, we're getting the coordinate. So if we move on to the upper left corner, we're getting something close to 0, 0. Go to the lower right corner, we're getting something that's close to 720p, right? So that's all good. It's all good. We do have a problem though. When we move the cursor away from the viewport, those numbers stops updating, and that means we actually cannot go too far, right? That wouldn't work because we want to continuously move the camera even the cursor is indeed outside of the window. So we need to basically tell the window to capture the cursor, right? Once the cursor is in there, it's in there, right? Just like you really just keep on going, right? Even the cursor is not in the window. And we need to do that by doing a glfw set input mode, and we're of course setting that to our window, and then we're going to set something for the cursor, of course, and then glfw cursor disabled, right? That will tell it to not show cursor, and whenever cursor moves, it moves, and then the value will be calculated, right? So if we run this again, right, we can drag this over here and then have our console moved here, right? You can see we're actually able to move to any value now, right? It's capturing that movement, and almost assuming that the cursor is in kind of like an infinite world. It can move freely in whatever value you want it to be. Alrighty, so that's something needs to be added here to capture the cursor position correctly. All right. Once that's over, then we can go ahead and start setting up the calculations to calculate the direction we need to go for. However, we need to actually alter the value here at the camera directory or direction. So that thing has to be, to be a global variable if you wanted to access that in that function. So let's just move them over. It will be maybe we can use like a class to manage all those things. But in this case, let's just talk about the basic algorithm before we maybe organize the code if we have more time in the future. But for now, let's just put them into the global section. Okay, global variables. And then we're gonna try to calculate how much we have moved on every update here. Okay, and in that case, we can go ahead and have some doubles. Previous mouse position x, right, on b equals to 0. We start with in the center, of course, double previous mouse position z equals to 0 as well. Right, so that's going to be the two positions, and then in that case, what is z? That's y, right? We're doing x and y, and then we can calculate how much they're differed by doing or creating another double offset. V equals to x position minus previous mouse position x, right? And double x offset, then x offset, lowercase x, I guess it's easier. And then the other one will be y offset, will be equals to y position minus previous mouse position y. So we got the offsets, right? And then we update the positions. So previous mouse position then becomes the current mouse position, so that when we move on to the next loop, next update, right, that they're gonna get the correct information. All right. Okay, now once we have that, right, we can then start to calculate the actual angle. Right, we can use those angles and use some trigonometry to get things calculated, right? So eventually we need to get a vector, right? That's indicating where the camera is looking at. Okay. And so because of that, I need to also get a reference of the actual yaw and the pitch. Okay. Now this is when things getting a little bit more interesting. Okay, so because we need to calculate the values, right? If I try to draw something out, right? So if let's say we have basically a coordinate system like this. Now this is the x and this is the z. We're looking at our 3D world from top down. In the default settings, our camera is actually looking here. Okay, looking here, that's negative z, right? It's negative z. So if we wanted to use some trigonometry, it's better to actually thinking about an angle that's starting from here, right? And that's going to be the angle, alpha, or in this case, the yaw. Yaw meaning you're looking left and right. Pitch is looking up and down. We don't really worry about anything else. We don't really tilt the head. We don't really tilt the camera angle, so that's irrelevant. We only care about those two rotations. Yaw, again, looking left and right. Pitch is up and down. So this is our yaw, right? If that's our yaw here, right? Y. Now in the default settings, our yaw is not pointing there. We're pointing to the negative z. Right, so our yaw is actually something can be negative 90 or 270, right? Whatever you want to use, all right? But it's actually this angle. Okay, negative 90 is going to be where we start, all right? If that makes sense. So here, that's going to be equals to negative 90.9. Pitch, of course, will be equals to 0. We're not gonna look up and down. Okay, and then we can just offset the yaw and pitch. So yaw plus equals to x offset, and the pitch plus equals to y offset. So we're offsetting these two things. However, we also wanted to have a scalar to kind of like define the speed of the rotation. So we can do another float here. Call this guy camera rotation speed, right, equals to 0.01 maybe. Just make it kind of subtle. So then we'll need to multiply with that just to scale this down to something that's not moving too fast. Okay, right? That way we're basically updating yaw and pitch based on the movement of the cursor. When we move left and right, which is the x direction, the yaw get offsetted. When we move up and down, the pitch is the one that's getting offsetted. Okay. All right. The one thing to be aware though is that if we don't limit the pitch, we can actually go overboard and looking straight up, or even looking like you're bending the whole body backwards and looking back, right? That will actually cause the axis to be flipped because we do rely on the up vector to always be looking up. Okay. So we're going to limit the pitch. Okay. So pitch will no longer be bigger or bigger than 89 and smaller than negative 89. So pitch, right, will be equals to pitch bigger than 89. Oh, not 8.9, 89. Right. If it's bigger than that, then it's going to be equals to 89, right? Or it equals to itself. So we're basically make it no longer, or we're basically limiting it from getting bigger than 89. Okay. And for negative values, we just do the same thing, smaller than negative 89, right? If that's true, then we make it equals to negative 89, or we make it equal to itself. That way we're limiting the pitch to not go overboard. All right, now it's time for some trigonometries. Again, if you just go back to our previous diagram, right, we can think about, hey, well, right, this is x, this is z. Now this is, of course, the current starting point, right? That's where we're looking at for now. Now let's say we're looking at, here, right, instead of there. Again, this is our yaw angle, right? The yaw angle. Now we can easily say that, okay, x will be cosine yaw, right? So x will equals to cosine yaw in degrees, right? And then z will be equals to sin yaw, right? It's a very simple trigonometry here. So we need to go ahead and apply that. Okay. So let's type that in. I'm going to create the floats. Direction x will be equals to cosine, right? Or using cosine yaw, but that has to be converted into radians because this cosine function takes radians. So we need to change that, and then that's yaw, right? And floats direction z will be cosine GM radians. Okay, and then also, oh, actually this is going to be sin, right? The other one, sin yaw. Okay, and then floats direction y, however, right? That's going to be on the vertical direction. Now that has to be, that's actually easier because we just have, so this is y, right? And that's whatever value that is. The pitch value, the angle will be here, right? So, how much we go on the y will be basically the sin pitch, right? This guy here. So that's going to be equals to sin GLM underscore radians and pitch. Okay. All right. However, this is not the whole story though. When you look up, right, the other two axes, the x and z, will have to reduce. So whenever direction y get bigger, we're looking more up and down, and then left right will have to scale down, right? Otherwise it cannot really go too far. So we just need to scale those guys down by the cosine of the GLM radians with our pitch. Okay, and do the same thing to the z as well. So that way we're scaling the other two axes down if we have the y-axis to go up. Okay. With those calculations, we can just say camera direction just equals to GLM normalized version of the 3 vector values we calculated already. So direction X, direction Y, and direction Z. Okay, so normalize the version of that. And then we can do another, oh yeah, we don't have to do another, we just need to define the camera right that we're already calculating. We'll just recalculate the same thing. That's going to be GLM again, cross product, right, of the camera direction, right, and then the camera up. Okay, alrighty. So that should give us a proper rotation update. So let's give this a try. I can see we're kind of doing something, right? When I go look left, look right, I'm really changing it. Up and down is actually the offset. So we probably need to reverse that. Right, whenever you see something that's reversed, it shouldn't be too hard. We just change that pitch to, minus equals to 1 to reverse the y-axis. That's very common, right, in real practice. Right, so now it indeed is giving us what we need. Okay, left and right, up and down, all looking good, all correct. Very nice. So yeah, that's basically how you set up the control. Right, to make it, to look at the direction you want to look at. And that's it. That we can now use everything we have here just to look around the whole scene, right? No problem. Okay, we can have a bunch of various different cubes and other models. We can set up lighting and everything. Now this can already be a basic framework for like an interactive 3D environment, right? You can do a lot of other things with it, but that's the basic navigation control. We can actually have one more thing to make it work slightly better. In the very beginning, when we move the cursor in, it can be in any position that could be further away from the center, even we say that's starting with center. So one thing we can do is to make it not really do anything in the first go and just update the position of the mouse. Okay, so we can create another boolean, first in tray, right, equals to true, and then if first in tray, right, we're gonna say we're gonna basically update that, and then we're gonna say first in tray equals false. Okay, that way we're able to prevent it from kind of like jumping, if that makes sense, right? From jumping when you first get into the viewport, and this will be a bit more stable. All right, that's actually 80 minutes. Rotation is always more difficult than movement control. When it comes to rotations, right, you need to do a lot of calculations. Sometimes you got something kind of wrong and it's hard to fix. You can also see like when I try to look up, right, it's kind of like got stuck. It doesn't go further than that. Same thing goes for you look down, right? It's going to lock it to that particular angle, which is 89, before moving too far. So this will be fairly stable. Alright, yeah, that's it for this video. Thanks for watching. So I'm thinking this is gonna be it for this tutorial series, just to get you up and running with OpenGL for the very foundation. We haven't go far with shader. We probably haven't talked about anything like lighting. Our code is not that much organized, right? So if I have more time, I may keep on going with this. Maybe do some refactoring of all the code we have, right? Because they're kind of like all over the place and a lot of global variables. Wouldn't be nice. So if you wanted to, right, go ahead and do your organizations. Use classes to, manage those various variables. Maybe you can create a camera class, a shader class that takes care of the shader creation and attribute assignment. You can even create specific functions that pass in pass in variables using uniform, right? Those can all be done with object-oriented programming and have better organizations, I guess. All right, that's it for this tutorial series. Thanks for watching. See you next time.